everyone. It's 1 o'clock, and we're at lecture 4 of our cosmology series. Got some fancy artwork here from the Hubble Space Telescope, star-forming regions, and a very dramatic set of dust clouds where stars are being formed. So we're going to talk today about the dark universe. We've been over this kind of expansion model that dates back to 2017. I looked this up. I think that's correct. This is the version that existed back then, and it shows the key features of the evolution of the universe, including this big period of dark age where there were no stars. We've also looked at the concordance that we get related to the amount of dark energy and matter in the universe, which includes merging data from a number of independent astronomical enterprises to try to narrow down where is the universe sitting right now. And we have this spot right there, which gives us roughly 70% dark energy and a total matter in the universe of 30%, of which about 1/5 is atomic matter, stuff we're made of. And we get the same number when we look at our model of Big Bang nucleosynthesis. That is,
excuse me, your slides are not being displayed.
Oh, thank you for telling me that. Let's get that. What has happened? Stand by for action. What's going on? Okay, I think I see the problem. How about now?
That is good.
Okay, so let's go back. This is the picture I was talking about, star formation. So we have, this is our model of the expanding universe. Concordance tells us that about 5% of the universe is baryonic or atomic matter. Those are synonyms. And we get that from this kind of curve. Understanding nuclear physics as we do today, we can predict how much of different elements, particularly light elements, that we should see when we look at galaxies. And indeed, we come up with a number of 4.5%. So agreement is there. And then I showed this curve that compares this green line, which is the calculation resulting from Einstein's theory of gravity, if you use these two values, dark energy at 70%, dark matter at 30%, and you see the green line shows where we should see galaxies if we go out and measure. And these black dots are actual measurements. So this is the pie chart that applies to our universe. We have a little bit of neutrino action that doesn't affect us. Neutrinos fly through us. Billions of neutrinos per second passing through your body, coming from the sun. This is the wedge that we all live in. Mostly that, by the way, that 5% of the universe that's made up of atomic matter is dominated by gas between the galaxies. Hydrogen and helium just floating around, not contributing, being very lazy. And right here, this little green wedge is all the matter in the stars. And the planets are so small in consequence. I mean, we know about, of course, the planets in our solar system, and we know about a few thousand planets we've found in other solar systems. But if you put all of them together, be insignificant on this chart. the bulk, is dark energy here and dark matter. And that's what we're going to talk about today. Here's the partitioning of the pie chart. So let's talk about what we mean by dark in this context. And I have a few pieces of artwork to keep us entertained. I'll talk about this one particularly later. So we have dark energy, we have dark matter. For the purpose of this class, I've put black holes into the category of dark. Now, the black holes are invisible to us. The specific entity that defined by Einstein's equations is black. It doesn't do anything. However, virtually every black hole is surrounded by a cloud of debris that's in orbit around the black hole. Some of that debris, most of it, eventually will get sucked in and become part of the black hole. Some of it will be thrown away just because of the dynamics near the black hole. And that disk of gas and dust is at stupendously high temperature, millions of degrees. And that radiates, so we can infer the presence of the hole by looking at the behavior of the radiation coming from the accretion disk. We also can infer the presence of the black hole by looking at the motion of visible stars near the black hole. And this has resulted recently, in the last 10 years, for a Nobel Prize for persistent observation of stars near the center of our Milky Way galaxy. And from that, we can look at the trajectories of the stars very deep in the center of our galaxy and do a little arithmetic, and we get the mass of the black hole that is ours. And it is not a supermassive black hole by some standards. That's just a name, but it's 4 million times as massive as the sun. And it's kind of at the low end of what we've seen in other galaxies. I think the world record is about 30 billion times the mass of our sun in an ancient galaxy. So we'll be talking about black holes. We'll talk about neutrinos. That's why this image is here. This is a view of the interior of a neutrino detector, that these things that look like disco balls are actually photodetectors that, when the machine is running, are all submerged by ultra pure water. And you see that's these are human-sized humans. So you see this is a big cavern underground. You fill it with ultra pure water, and very, very rarely a neutrino interacts with matter, and the resulting debris is detected by these phototubes. Here's an example of how neutrinos avoid interacting with matter. They're coming out of the sun, as I said, in just stupendously large numbers. The distance a typical neutrino can travel before interacting with the material lead, which is a very dense material for human standards, 100 light years of lead before a neutrino interacts with a lead atom by accidentally crashing into the nucleus. So 100 light years is about how far a neutrino can travel through lead without interacting. So this depicts a laboratory for detecting neutrinos. I already mentioned dark matter. This is results from lensing of distant light. And by detailed analysis of that, we can see clouds of dark matter floating around between the galaxies. We'll talk more about that. Of course, here's the pie chart. And this is what a black hole looks like in theory. And we have images now. We will, not today, but next week. Yes, next week we will talk about a revolutionary new scheme for actually imaging the debris cloud, the accretion disk that goes around a black hole. And we have photos of black holes. That's brand new in the last 10 years. So let's talk about dark energy. In a prior class, I mentioned that when Einstein's theory of gravity was finally mature in 2016, he was at that time, he was one of the many people who thought the universe was static. And his equations predicted a dynamic universe, one that could grow or shrink. And so he postulated a slight adjustment to his equations, to make sure that the universe would stand still. Just 10 years later, the Hubble results showed that the universe, in fact, is dynamic and it's expanding. But already, because Einstein was trying to keep the universe in a static state, he had invoked what he called a cosmological constant. And we now call that dark energy. There are other names that are used. Now, in the past, I have shown you, or I've talked about, the biggest challenge in measuring the expansion of the universe that was pioneered by Edwin Hubble. It's not so hard to measure velocity of distant galaxies, but it's really hard to measure their distance because we don't have a big yardstick, but we can create what we call a cosmic ladder. And this depicts the technique. And it's a mess, but I'm going to walk you through it. So here we are in the local neighborhood. This is the brightness of objects that we're going to look at. And the Milky Way is right on this distance scale. Notice this thing, it flew in. I'm gonna let it fly in a second. But the little green dot there represents, here we are on planet Earth, and this is where our telescopes are located. And we have various objects whose distances we can measure using parallax. That's a geometrical method for determining distance. And one of those dots is the Milky Way itself, the distance to the most distant objects in the Milky Way. And we have the Large Magellanic Cloud out here. As I go along this diagonal line, I'm getting farther and farther away from planet Earth. So the Large Magellanic Cloud is in orbit around the Milky Way. And we're going to put a scale on here in a minute. It's not on there yet. Then we have the galaxy M31. And so you see these green dots. This all comes from geometry and the use of variable stars called Cepheid variable stars. The combination of being able to use geometry as Earth goes around the sun and observing how these various objects appear relative to much more distant objects, that calibrates the distance to the Cepheid variables that we detect because they have periodic brightening and dimming. And the important thing here is that knowledge of how the brightness of a pulsating star relates to its total energy output can be used to calibrate the distance to type 1a supernovae. I talked about those last week. These are well understood explosions. We understand the radioactive products that come from those. And by careful analysis of each explosion that we see in distant galaxies, we can we can measure the distance to those explosions by exploiting the Cepheid variables in those distant galaxies, because we know they're the same as the Cepheid variables that are nearby and whose distance we can measure using geometry. So we're just taking one step at a time. So here's the supernova brightness, SN1A, that's written there. So that brightness gives us this continuation of this distance scale. So we get from the Cepheid variable brightness, we can infer the supernova distance by looking at its brightness, and we get these examples. The Hubble Space Telescope, when it was repaired in 1993, ended up producing good supernova data for for type 1a supernovae in a catalog that contained, I think, 27 such stars, exploding stars. This curve was drawn probably 5 to 10 years ago, and we now have, and these are the points, these blue points come from the Hubble Space Telescope investigation of these exploding stars. James Webb adds to this, and it adds a whole bunch more dots here. Then, if we know the distance to type 1a supernovae, then we can infer the expansion rate of the universe. And there's an example of the value. And I've already explained there's still controversy about our knowledge of the so-called Hubble constant. This set of data used a version of data that produces a Hubble constant in the low 70s. Later today, we'll talk about better estimates and how that work to resolve the Hubble tension is progressing. So we have this line. Oh, and then we get, these are supernova events from James Webb at the most, for the most distant of these supernova events. And these relate the redshift, that is the velocity of those objects, to the expansion rate of the universe. So we have this big long line. So let's add some more detail. This is, along this line is distance. And we're going to add some here in a second. This just covers what I've been talking about. So here we are with an object right behind this heavy arrow, 3,200 light years from us. Remember, the Milky Way is about 200,000 light years in diameter. So this is an object inside the Milky Way. Here we are at the Large Magellanic Cloud, 158,000 light years, right at the perimeter of the cloud of stars called the Milky Way. And we go to M31, 2.5 million. So this M31 is well outside the Milky Way. And all this is coming from exploiting the geometry that we get from observing these objects and the variable stars that are contained within them. This galaxy is 20 million light years away. Now we're going to introduce Z, that's the shift in spectrum induced by the recession of the galaxies that Hubble first detected. And the term that is used, starting at about this point, where we actually detect a value for the redshift, it's called the Hubble flow. Any object closer than about this number, 100 million light years, is moving away from us so slowly that we can't assign a value. It's hard to do science with those objects. But when we get out here, the redshift is, well, you see the number there, and we're out beyond 100 million light years to these various supernova events, the blue dots. If you go all the way out to this point, now we're at 200 million light years out into the universe, and there's the redshift that pertains for objects there. At 1 billion light years, we have a redshift of about 7%. And right at the limit of the observations done with Hubble and James Webb, we're at a redshift of 1.3, and the distance to those objects is about 9 billion light years in a universe that has existed for 13.8 billion years. This is where we stop because the images obtained this way by using this ladder are becoming so dim that it's difficult to see farther out. But James Webb is helping us get out there. And by the way, at a redshift of 1.3, you're about at the point where these distant objects are receding from us at the speed of light. Farther out, they're going away from us faster than the speed of light because of the expansion of the universe. Now, there's been improvement. I mentioned that the Hubble Space Telescope had a couple of dozen supernova events that were used to actually they were the ones that were used to detect that the universe is expanding at an accelerating rate. That's this data. And James Webb provides even more refinement of that data set. And you can see the Hubble data is the dots, the red dots there are measurements of various 24 or so supernova events. And there is some fuzz there. You can see if you draw the best line through there, there's some variation along that line. Here's the James Webb data, and it's tightened that up so that the Hubble data was good, and the Webb data is even better. And here's the world record now from James Webb for redshift at 2.9. Remember, on this ladder, the farthest out we get is a redshift of 1.3. But here's a reference to new results from James Webb with a redshift of 2.9, which puts us off of this chart. This chart goes 38, 40, 42 in brightness would be about here, but now we're looking at a value of 47, so it's off the top of the page. The other thing that has happened is that people have gone back to the work done in the early 20th century by Henrietta Leavitt. And you may remember I described her effort to characterize Cepheid variables. And this is the data that comes from a paper she wrote in 1912 with a colleague showing two dots for each star. This is the dimmest that star exhibited, and that's the brightness of that star. So you see all these are, if you draw a vertical line, you're looking at the dimmest and brightest in each case. And those brightening and dimming data are related to the period in days of the star. And most of these are oscillating on a period of a few days to a few months. And the result is this gives us a calibration of the brightness of a star as a function of its period of dimming and brightening. This paper, or her paper of 1912, has now been updated 10 years ago. And the new data is included in a paper that came out early this year. One of the authors is Adam Rees, who won a Nobel Prize for determining that the universe has an expansion rate that is accelerating. So there's been a renewed interest in refining Leavitt's work 100 years later and using better data from much better telescopes. And there's some technical mumbo jumbo here that it's there for my reference, but this is what a typical star looks like when it's brightening and dimming. I don't know the time scale there, it's probably weeks. So we're not done refining our understanding of Cepheid variables, and we'll see more about this later this afternoon. So here are the people that won in 2011 for detecting the expansion rate of the universe. Saul Perlmutter at University of California, Brian Schmidt at MIT, and Adam Rees at Johns Hopkins. And here's what their data looks like. This is the result from Perlmutter's group. So they're looking at redshift, that is the velocity curve, and the brightness of a variety of galaxies. Now, the way astronomers handle this is a lower numerical value is brighter. And so we see here data collected from a ground-based telescope prior to the results being published in the late 1990s. By 1996, the Hubble Space Telescope data were not mature yet, but this ground-based telescope in Chile produced these results. And you can see you can't draw any conclusion about a trend line other than if you draw a straight line through the data, that's the other end of that straight line. And if that's all the data you have, then you can read off what that implies. A universe that lies on this straight line from that point to that point has no dark energy. That's what that zero means. That the dark energy is zero and all the energy in the universe is in the form of matter. And it took the emergence of the Hubble Space Telescope data to help us see the curvature in this line. And you can see for sure that there's a clustering of these red dots coming from supernova events that's different than this. This is part of that straight line I mentioned right there. Most of the dots are above that straight line. So that means we're talking about universes where the amount of matter is not 100%, and the amount of dark energy is not zero. So as we progress in steps up along this curve, these various possible curves, we're introducing the possibility that the energy in the universe is a partition between matter and dark energy. And when this paper came out, this is from Perlmutter's paper in probably 2004, 2003, you can see where we're starting to see the implication that ultimately led to the right value, which is right in that gap at 0.3 for matter and 0.7 for dark energy. So it's this clustering of data here that sounded the alarm bell that the universe is not dominated by matter. Well, we can redraw this, and it's easier to see on this, what's called a logarithmic scale. It's the same data. And here we have the redshift this way and the brightness of the objects this way. And you can see this solid curve is the one you'd have if the universe was fully occupied by matter and had no dark energy. And it's clear from this that these supernova events tell a different story because they're all above this solid line. There's one or maybe two examples that don't. But out of these 20 or so events, there's clearly an implication that the universe has dark energy. And this led to the Nobel Prize. Now, here's the same supernova data from Hubble in the late 1990s, manipulated by Adam Rees's team and the team at MIT, using different processing techniques. So here's Perlmutter's data is the the red dots. And Adam Riess's data are blue dots. Again, we can see there's some curvature in this line. And here's the Cerro Tololo measurement from the ground. And here's on this curve, this solid line is what we now know to be the truth. 30% matter, 70% dark energy. And so this is where the dark universe revealed finally that the universe is expanding and the rate of expansion is accelerating. Now, there's more to dark energy than the expansion rate. Here's I showed this last week. If you use the supernova data, you see that the size of the universe is increasing at an ever increasing rate, that objects that were close together in the past are now far apart. In addition, the light that was produced by the supernova events that we detect has been stretched. That's the Z factor. It's been stretched because during the flight of the light to us, space has expanded and it has caused that light to stretch. But dark energy, so this is what the two groups back in the late 90s teased out of the supernova data. But there's more to the data. We get this expansion rate that's accelerating, but we also get a new way to estimate the age of the universe that's consistent with what we see from the cosmic microwave background. I've talked a lot about the microwave background. The microwave background was not used to do this science. This is all comes from supernova events. In addition, the expansion rate of the universe is related to something I have talked about 2 weeks ago. And that is that the microwave background shows us where the densest and less dense regions of the universe were right after the Big Bang. And that's where we see concentrations of galaxies these days. They are essentially like little valleys that would attract matter and dark matter into clusters, which ultimately led to the formation of stars and galaxies. And that's what is called baryon acoustic oscillation, because these dips in these changes in the density of the universe are changes in the atomic matter, the baryonic matter, in an age when there were sound waves in the universe, where the universe was much, much smaller and disturbance in one spot would propagate like sound waves that are traveling from me to you right now. In addition, this dark energy explains through the cosmic microwave background why we know with high confidence that the universe is geometrically flat. It turns out that a critical factor is that the fraction of the fraction of matter, including dark matter and dark energy, if you add those together, you get the number 1. And in the Einstein equations, when you have this value, a value of 1 for what is called the critical density, that immediately tells us the universe is geometrically flat. And so these pieces of the pie chart that I showed a few minutes ago, adding up to the number 1, tells us the geometry of the universe, not the shape. We don't know the shape, but tells us the geometry. And then there's additional information coming from other sources that complement the idea of dark energy in the universe, including the X-ray spectrum of certain galaxies and the derivation of the Hubble constant, which is shown here. So it's not just one thing we get from a universe that's 70% dark energy. We get a variety of other results that we can compare with measurements from the cosmic microwave background, the density of galaxies at different ages in the universe, and so forth. So here we have the expansion rate of the universe. This is a form of a graph I showed you last week, a little different. Here we are right where the red dot is. This shows that the expansion rate in the early universe was higher than it is now. And using the Friedmann equation and the idea that there's 70% of the energy in the universe is dark energy propelling expansion, we see the influence of gravity in the early universe when the universe was small, but as the universe got bigger, just at this point, about 7 billion years after the Big Bang, the universe was big enough for dark energy to become the dominant factor in the growth of the universe. And we've had growth since that time to the present day, and we expect the expansion rate to continue to grow. And this curve is a version of what I showed a minute ago, that if we use the values that we now have for matter and dark energy, we get good agreement with measurements of the properties of distant galaxies. Now, a question is, where does dark energy come from? It's a confounding problem for modern cosmology that we don't know why the dark energy exists, and we don't know why it has the value that it has. The interesting thing is that the value that we find is just right for an expansion rate of the universe so that there's time for planets and stars and planets and us to evolve. If the density of dark energy was much bigger than it is now, the universe would have gotten so big so fast that stars might have formed, but it would have been difficult for galaxies to form because the stars would have been speeding away from one another so quickly that the influence of gravity would have not been felt. So one pioneering effort comes from Casimir, who in the late 1940s demonstrated something I talked about last week, that empty space contains energy. And there's some really entertaining criticism of his work by famous people who thought he was completely nuts. And the idea is that if you create a vacuum by managing to make the universe bigger by some, say, mechanical means, you just get some diabolical genius to stretch the universe into a larger volume, dark energy spontaneously appears everywhere so that the density of dark energy stays the same. And so Casimir was working in the realm of quantum physics and made his prediction that an empty volume would have virtual particles popping into and out of existence. And as I say, he was criticized, and it took 50 years to actually build the very exquisitely detailed experiment to actually measure these quantum fluctuations that he predicted. And it turns out he was right. There's Casimir, predicting that if you put two plates in an experiment very close together, that the long wavelength virtual particles that might appear can't fit in this space. So the spaces around the tiny space between these plates there would be a force. A way to think about this is if you go skiing, you go up to high altitude and you drink a Pepsi or something, put the lid, empty the bottle, and then toss the bottle in the back seat of your car, as I often did. On your way down, you hear groaning and moaning as the increasing pressure as you descend into Denver. The air pressure will crush the bottle because the bottle, relative to high altitude, the bottle is essentially empty and higher pressure will crush it. And this is the kind of mechanism that Casimir had in mind. And here, the solid line is his theory, and these little squares are the measurements. And there's a little adjustment that has to be made because the shape, the experimental shape that was chosen didn't have flat plates. It had curved plates, but that's a minor detail. So Casimir, it turned out, was right. So we have a number from Casimir for the amount of energy that exists due to quantum fluctuations related to subatomic physics. And here's a kind of a cartoon of what this business of quantum foam looks like, just particles and light with no apparent source, just popping into and out of existence, allowed by the Heisenberg uncertainty principle, which is depicted this way. So physics says that these particles can, indeed, they must exist. They must pop in and out of existence without any known specific source. And at this point, astronomers might have concluded that if there's dark energy in the universe, it comes from the Casimir effect. So we have astronomers measuring the energy in the space between galaxies by looking at the expansion of the universe, and they get a number. And you can compare that number with Casimir's number. And we know Casimir's number is right because we've measured it. So the astronomer here is saying, hooray, we measured the expansion rate of the universe, and we know how much energy it takes the universe to expand at the observed rate. And the laboratory people say, yes, and we've measured vacuum energy based on the Casimir effect. Well, let's compare numbers. And it's not good. The difference between the estimates made in the lab for vacuum energy due to quantum mechanics and the astronomer's value derived from the expansion rate of the universe is wrong by this number. That is a big number. Indeed, you can find lots of versions of this kind of quote, that this is the worst prediction in the history of physics. Nobody understands why subatomic physics, confirmed in laboratories, predicts energy in a vacuum, and the astronomers find a dramatically different value. And luckily, I'm going to repeat myself, luckily, the value of the astronomers measure is the small one, is 10 to the 120th times smaller than the vacuum energy measured in the laboratory in this experiment. Otherwise, the universe, as I said, would expand so fast that you'd never have galaxies and production of heavy elements, and we wouldn't be around to make observations. And so this is 10 to the 120th. There's 120 zeros there, and all we can say is we just don't know why the energy density propelling expansion in the universe is so tiny compared to what we might expect. So the question is, why is it so small, and aren't we lucky? And over the last year or so, we have new results being teased out by an instrument looking at large numbers of galaxies and refining how the expansion rate is measured using galactic data. And you'll see results here from early this year. This dark energy survey produced a result that implies that the dark energy density, not the total dark energy, but the density, sort of like, well, let me compare it to, if you probably remember from high school chemistry, that the density of water is a gram per cubic centimeter. That's a measure of density, how much energy is in a specific volume. That dark energy density, based on this new set of results this year, suggests that the dark energy density is changing with time. And that's a area that needs a lot more attention, because if that's true, it has implications for the evolution of our universe. But for now, until this work is brought to maturity, for now, the assumption is that dark energy density in the universe has been the same since the early universe and will continue to be the same in the future. And we have many ways to see the implications of a constant dark energy, and our models agree with measurement. The idea that dark energy density can be changing has always been available to astronomers, but now we have some evidence that it might be the case. So that complicates things. So now let's talk about dark matter. Here's one of the pioneers of the search for, or the proof of evidence of dark matter, Vera Rubin, who studied galactic dynamics. 2 lectures ago, I showed you that using the redshift, we can tell what the rotation rate of galaxies is. We can look at one side and the other of the galaxy and see stars approaching us and receding from us. And because redshift tells us velocity, then we can get the velocity of rotation of the outer stars of a galaxy. And that's what Vera Rubin did starting in the 1960s. She wasn't the first, though. An eccentric astronomer, Fritz Zwicky, in the 1930s had already seen that not rotation rates of galaxies, but the dynamics of galaxies that are bound together by gravity. So if you have a cluster of galaxies that has, say, 1,000 galaxies in it, you can, using redshift, you can see how those galaxies are moving with respect to one another. And he had already suggested the idea that there's some type of matter in those galaxies, in those clusters, that is invisible, but it must be present. Otherwise, we would not see the galaxies in a particular cluster moving the way they do. So he was the first, and then Vera Rubin, who these days gets most of the credit, but Zwicky preceded her by about 30 years. There's other evidence too. Looking at the velocity of stars, not galaxies, but actual individual stars in tiny galaxies called dwarf galaxies, the presence of dark matter cannot be avoided. It must be there. It's influencing the motion of stars in the galaxy. We can also measure the flow rate of gas in between the galaxies that form a cluster. Remember, a cluster is a group of galaxies, just like a galaxy is a group of stars. But in a cluster, there's gas, not confined to the galaxies in the cluster. And that gas, the flow of gas, can be detected. And it also implies that there is an unseen material something that has gravitational behavior, but does not interact with light. We see this also in interaction of galaxies within clusters and outside of clusters. And gravitational lensing also reveals the presence of dark matter because the dark matter changes the trajectory of light moving toward us from distant galaxies. And I showed this before, I'm going to show it again. We can actually map out the presence of dark matter by using lensing data. And I think on the next page, you're going to show examples of collisions of galaxies and the behavior that has occurred when we look at those collisions can only be explained by some sort of matter that doesn't interact with light. So it's not atomic, but it dictates how galaxies behave when they collide. So there's Fritz Zwicky. Here's a telescope that's coming online right now, named for Vera Rubin, who's no longer alive. So here's the kind of thing that Vera Rubin saw. Here's a galaxy, and this graph is centered. This intersection right here is for good reason. That point is centered on the center of the galaxy. And then what Rubin and her students did is measure the velocities of these stars at the perimeter of the galaxy. If you get too close to the interior, then there's so many stars and so much dust, you can't see the velocities of the individual stars. But out here you can. Here's her graph, observed values of the velocity of stars as a function of distance from the center of the galaxy. And you see she's got actual starlight, just doing telescope work, tedious telescope work, because this was done before electronic cameras were used in astronomy. So you're taking photographs and then having your students measure the density of the exposure of the photographs. It's nerve-wracking work. And then using a different technique, you look at the gas out here in the perimeter, where you're not actually looking at starlight, you're looking at the flow of gas that is not within stars. But you see these points all seem to be part of the same curve. If you then use physics to say what should be the velocity of stars in the perimeter of a rotating galaxy, you don't get this. You get this curve. That presumes you're only using the light coming from the stars or the gas, the hydrogen gas. And the difference is dramatic. There's something else going on. And this curve can be explained if there's a whole bunch of unseen, non-visible, non-atomic matter exerting its gravitational influence, but not interacting with light. So that's Rubin. Here's the issue of galactic clusters with dark matter, invisible dark matter, creating these distortions in the way the light progresses through this galactic cluster. This particular cluster has several hundred galaxies, gravitationally bound. We know they're in proximity because all these galaxies have the same redshift, so they're all receding from us at the same rate. In addition, we can, using supernova and other techniques, we can measure distance to these galaxies, and they're all together. I mean, that's a non-trivial thing to deal with, because when you look at the night sky, you cannot tell if a light source is close to you or behind a nearby light source. So galactic clusters, these are the techniques that are employed to determine that all the galaxies that are in this cluster are all neighbors. And from that, and I've shown this before, that we see these supernova events where these little circles are here and here. James Webb Telescope is now contributing to the database. of the distortion of distant galaxies by intervening galaxies. And the distortion is not just from atomic matter. It is the distortion, these lensing events, are the result of all the matter in the intervening galaxy, and that includes the dark matter. So we get these things like Einstein rings and so forth. So this is a depiction we've seen before. Here's a very distant ancient galaxy, a quasar fueled by a supermassive black hole, producing so much light that we can detect it here near Earth. But in between, there's some kind of galactic structure. We can actually make a 3D measurement of where is the matter in this intervening galaxy so that we see these four mirages, like this one. By the way, here's a almost perfect alignment with an almost circular galaxy. So if you have a perfect circular galaxy here like this, and a distant quasar light source and our telescope all on the same line, you would get a complete Einstein ring. And a few of those have been found. So there's, just like in dark energy, there's new developments. And when you get this PDF, you already have access to it. Anything that's in a red box is if you click on the picture, you get led to the reference article that led to this summary. So we see different new ideas coming. We have a new telescope called the Nancy Roman that is going to be used to further understand gravitational lensing so that we can map the location of dark matter more precisely. And there's even a suggestion for new type of dark matter. Right after the break, we'll talk about the different kinds of dark matter that have been proposed, because there's roughly 10 different types of dark matter that have been suggested that have gravitational properties but don't interact with light. So we're about to take a break. This would be a good time to see if we have a couple comments here. Oh, yeah. So no technical questions, unless somebody wants to pop up right now before we take a break. Okay. So when we resume at, let's say, 5 after 2, we'll talk about something you've seen before, but I'm going to emphasize in a way we haven't in the past, and that is the location and height of these bumps in the cosmic microwave background data. Remember, the cosmic microwave background is depicted this way. This is a sphere around us as observed by microwave telescope out in space. If we take this data and measure the average distance between warm and cold spots, like between this is called the cold spot, then nearby there's a little warmth, and then over there's a little warmth, and so forth. If we measure for this entire database the spacing on the sky of the temperature variations, which are exceedingly small, but the spacing is critical too, then we get this curve. And the data points we get from the spacecraft data are right on this model of how the universe should behave if we employ the Einstein's equations for gravity and the influence of various kinds of factors, namely the amount of dark energy, the amount of dark matter, the number of the geometry of the universe, and so forth. And I showed you last week how the various results of this model can be interpreted. But the key thing we'll talk about after the break is the position of these points and their height, because that tells us how much dark matter is in the universe. So let's take a break. I get to get something to drink for a minute, and I'll see you at 2:05. Okay, folks, I'm back. Now let me just reiterate what I was saying before the break. If we have this body of microwave background data, this is obtained from the Planck spacecraft, a European project. If we take that data and manipulate it mathematically, we see these peaks. And these peaks are related to the spacing of the peaks, and their height is related to a lot of different things, including the acoustics in the early universe. I've already talked about the fact that there were sound waves still present in the universe when this data emerged from a cloudy environment and was able to travel for 13.5 billion years so that we could catch it. So the peaks are significant, the spacing of the peaks are significant, and so forth. And dark matter has its influence because it's a gravitational factor. It doesn't interact with light, but dark matter has gravitational properties, and that changed the way the cosmic microwave background radiation propagated through the universe over the lifetime of the universe. So we see the influence here, and it's this first peak relates to the density of baryonic matter. And remember, baryonic atomic matter and dark matter are different things. The total of those two gravitational factors is about 30% of the energy in the universe. But the atomic part, the baryonic part, is the least significant. This peak right here, what they call the third peak, or what I call the third peak, this is related to the density of dark matter. So all of this stuff goes into this kind of model. This is what I showed last week, the so-called lambda, that's the Greek letter lambda, CDM model, which is the most successful model we have today for describing the evolution of the universe. And lambda CDM means lambda stands for dark matter, and CDM stands for dark energy. Lambda stands for dark energy, and CDM stands for cold dark matter. Now, why is the word dark, the word cold in there? We already understand enough about dark matter to know that it's not relativistic. That is, it is not matter moving at enormous speeds relative to the speed of light. And the convenient way to describe that kind of material is that it's cold. If the dark matter was relativistic, it would have different influences on the behavior of galaxies and galaxy clusters and so forth. And so the choice was made to abbreviate the current successful model of the universe as one that has dark energy, lambda, and non-relativistic matter whose origin is unknown. And in a minute, I'll show you the different kinds of dark matter ideas that are floating around. I also mentioned that we have a mechanism for detecting dark matter unrelated to rotation of galaxies. So this is called the bullet cluster. And you can see why it kind of looks like a bullet. And "40 galaxies make up this cluster. And the cluster that we observe today is the result of a collision between two clusters millions of years ago. In this picture, the blue is in the inferred position of the dark matter that would cause this kind of distribution of atomic matter to result from the collision of two clusters, two smaller clusters. There's also some notes here about an alternative interpretation of why we see an alternative to dark matter for why we see the rotation curves of galaxies that we see. And it's actually mentioned on the prior page. So let me go back there. I should have mentioned it. It's a niche idea that only a few people had embraced, but the father of this idea, which is called modified Newtonian dynamics, is a very energetic, smart person who argues that we don't need dark matter to explain what we observe in rotation curves of galaxies. So this is abbreviated MOND. Now, MOND has a much harder time explaining why we have this distribution of observable matter after the collision of two small clusters. It's a controversy that will go on the sidelines. Most everybody believes that dark matter is a material entity that doesn't require us to change Newton's law of gravity, which would be a big step. Nonetheless, this is what we see in the bullet cluster, 3.7 billion light years away. And we detect this halo of dark matter from the way light propagates through this region to us. It's essentially lensing used to detect the cloud of dark matter, and there's no other way to do it. We cannot. This blue stuff is not observable. If you go outside tonight and look at the bullet cluster, you're not going to see this blue stuff. Okay. So we have some animations. We can look at one of them. The way these were handled is Robertson did a series of calculations for two small clusters that collide. One of them has cold dark matter. Another simulation includes the possibility that the dark matter is aware of itself through other than gravitational effects. A third model is yeah, I don't know what this one's about. And the third one is the bullet cluster without dark matter. If you have two, and you can see the two little clusters of how they're going to collide. So we can jump into one of these simulations. So you have, I'll repeat this, but you had a cluster of galaxies here and one flew into the neighborhood. And you get a result that's different depending on which one of these ideas you have in mind. So there's a cluster of galaxies. Here comes the interloper, and they collide. And if I stop it right there, if there's dark matter in the neighborhood of each of them, because dark matter's a factor in the formation of galaxies and galaxy clusters, then you get something that looks like, let me move this. Oh, wait a minute. You're not seeing that. Hold on one second. I missed something. I screwed up. I need to stop sharing, and then I'm going to share my desktop. That way you will be able to see okay. Now let's get rid of that. All right, I'm going to have to repeat. So let's do this again. I apologize. So let's reiterate. You should be able to see, this is what the bullet cluster looks like, the pink and white. That's what you observe with a telescope these days. Now, let's go to YouTube and look at the collision of two clusters with dark matter as part of the assumptions about the collision. And you get that. There's an area here that's dense with stars, an area there, and you can compare that with the observed state of the bullet cluster these days. But if you hang on, if you do the version of the model, oh, sorry, we got to watch a hamburger. Apologize, but that's what YouTube does. If you look at the other models that Andrew did, you don't see a result that looks like the bullet cluster. For example, this one. This is the one with no dark matter. And you see, it just has one bright area. If you use the one, oh, we get music too. If you use the one with dark matter, you get something that matches what is observed. Now, I don't want to make too much of that, but the point is, these simulations are scientifically based, and they result in a map of where the dark matter would be. And the result for colliding galaxies is compatible with what is observed. So here are other galaxy clusters with the same kind of behavior. They're not as dramatic as the bullet cluster, but it's colliding clusters. And you see, again, the pink is atomic matter as observed by telescopes, and the blue areas are the inferred location of the dark matter. And this kind of study has been done over and over again. You see here, 72 different galactic clusters have been studied, and they all imply the presence of a cloud, shown here in blue, of dark matter influencing the way these collisions unfolded. Now, one idea, and again, this is when you get the PDF version of this presentation, if you click on this, you can see more details. It's a complete article. And the idea is this: if we exploit something called the Fermi Space Telescope, it's an gamma ray telescope. If we witness certain kinds of events and take a picture with optical telescopes and with this gamma ray telescope, we could infer the density of dark matter in the vicinity of that collision. And there's a discussion there. This would tell us that a as yet undetected entity called an axion, these are subatomic particles, some people believe are the source of the gravitational influence of dark matter. You might see the decay of axions, which produces gamma rays. Gamma rays are seen by this Fermi Space Telescope, but you have to have the telescope has to be pointing in the right direction, because it would just be a burst of gamma rays coming from a location where a merger occurred. And as they say here in the title, if you could do it, if you got lucky enough to be looking in the right spot at the right time, it would only take you 10 seconds to characterize the gamma ray spectrum coming from this imagined particle. Nobody has ever seen an axion, but this imagined particle, if it exists, would decay and give a unique output that would reveal a possible candidate for dark matter. So here's some, I'm going to repeat myself. Here are some of the properties of dark matter. And axions allegedly have these properties. They doesn't interact with light. That's why we don't see these things. The material is not going at high speed relative to the speed of light. That's dark matter is not relativistic. And it makes up about 25% of the energy in the universe. The stuff of dark matter has to be stable because it existed in the very early universe. It can't be a radioactive material, for example, because radioactive materials decay over time. And it's been almost 14 billion years since the first influence of dark matter in the universe. And in 14 billion years, you would have expected a unstable material to have decayed away like we see in nuclear decay. Does not interact with itself. That is, the dark matter particles don't collide with one another and lose energy. And this is critical because the clouds of dark matter that have been inferred from various approaches, including lensing, show that these clouds are stable. A cloud of hydrogen, for example, if you put a cloud of hydrogen near each other, the atoms interact and they have a way to lose energy. Scattering produces light, and the light carries away energy, and the atom that allows hydrogen atoms to lose energy and fall together, eventually producing a star. That doesn't seem to happen with dark matter. And in fact, this line I just brought up is that ordinary matter can make galaxies because it can lose energy through collisions and the subsequent radiation that occurs when atoms, really the electrons in atoms, come near each other. It produces a glow that carries away energy, and gradually those atoms settle into a denser and denser region in space, and eventually you'll get a star. Dark matter doesn't seem to do that. It also means that dark matter probably can't fall into a black hole. Before the break, I talked a little bit about black holes. We're going to do some more here in a minute. That the accretion disk around a black hole glows very brightly. Well, anything that glows is losing energy. That energy is convenient for us for characterizing the behavior of black holes. And that's the mechanism by which atoms in the vicinity of a black hole can lose energy and fall into the black hole. Dark matter doesn't interact with itself. So if it is in the vicinity of a black hole, it probably just sits there and orbits around for all of eternity. So here's a little cartoon the NASA people put together. It looks like a box of cereal. The ingredients, it says no one really knows. If you figure it out, let us know. And the question is, would you eat this? So here are the candidates for dark matter. Some are solid candidates and some are not. And they all have funky names. So weakly interacting massive particles. They're called WIMPs. And there are various experiments that have been done to find particles that interact via gravity and what is called the weak force. The weak force is the force in physics that facilitates radioactivity. And so far, no convincing results for WIMPs. Here are the axions I mentioned. These are low mass, slow moving, that is not relativistic. They have no electric charge, because if they had electric charge, they would interact and we would see a glow from a cloud of axions. And So there are axion dark matter experiments and so forth. No, whoops, no results yet. Then you have larger objects, not subatomic particles like WIMPs or axions, but neutron stars or cold dwarf stars that obviously have gravitational influence, but they're baryonic. That is, they're made of ordinary matter, ordinary atoms. And that would, if they exist in numbers large enough to influence the rotation of galaxies, that would influence the peaks we see in the microwave background. And we don't see evidence for this. So the idea of cold stars or neutron stars making up the huge amount of the universe, 25% of the universe being in the form of dark matter, this idea is on shaky ground. Then you have a technical thing that could exist, it's never been seen, called the Kaluza-Klein thing that only exists if there's a fifth dimension to the universe. Remember, the universe in Einstein's way of thinking is four-dimensional, three directional dimensions and one time dimension. Kaluza and Klein back in the late 1920s, early 1930s, did a bunch of calculations on a five-dimensional universe. Is it possible that there's a particle that exists in that universe that could only sort of stick its toe into our universe and would have the properties of dark matter? That's highly speculative. And a gravitino is a subatomic particle related to the gravity force. The people at CERN in Switzerland have been looking for gravitinos. They should be able to produce them in their big accelerator, doing experiments in something called supersymmetric particles. No such item has been found. So it's a mystery. In spite of it being a mystery, we can map. Using lensing, we can map clouds of dark energy in and around galaxies that produce lensing effects. And this is what some of it looks like. This particular case, we're looking at distant light from a distant quasar coming to the Hubble telescope. And by looking back at different phases of the trajectory of that ancient light by using redshifts, you can build this map. So it's just an amorphous blob of stuff and nobody knows what's happening. Here's another one done by the Japanese. So we know how to map this stuff, but we don't know what it is. And the search is on. And it'll be a Nobel Prize for anybody who comes up with a compelling description of dark matter. Now let's talk about something black holes. To talk about this, if you wanted to do it right, you'd look at Einstein's equation. And the reason I have this piece of art or this piece of music is to indicate that when we look at equations like this as non-experts, all we can do is appreciate where the ink is. So I love this painting by Caillebotte. The way it's the subtlety of the lighting for these guys scraping the varnish off of a floor is really beautiful. But I have no idea how Caillebotte did this. It's sort of his level of expertise was so high, but I don't need to understand his technique to appreciate this. Here we have a piece of music by John Coltrane, same idea. There's black and white on this page. And if you play this, as I sometimes do, it's a beautiful piece of music, but I don't know how it came from his artistic mind. And this is Einstein giving us the same thing. But we can identify pieces of this equation related to the curvature of space-time, how energy and momentum play a role in the shape of the space-time around massive objects. And here's the dark energy component. I mentioned that Einstein put in to try to create a stable universe. Turns out we need this to explain the accelerating expansion of the universe. And the idea here is that if you have a massive object like these little eggs I've put here, it distorts the trajectory of light traveling because the energy associated with these three objects bends space-time, and that tells light how to travel. And John Wheeler, famous physicist, who's known for his quips, said space-time, which is four-dimensional, three dimensions of space and one of time, space-time tells matter how to move, and matter tells space-time how to curve. And you could replace the words matter here and here with light. That space-time tells light how to move, and light, intense light, also alters space-time, and you end up with this depiction of how a light beam might travel through this neighborhood, influenced by the presence of energy and momentum. So early in the 20th century, Einstein's theory came out in 1916. Right away, he had calculated how light would be altered in its path if you observed stars during an eclipse. So here we are on planet Earth, and if the moon obscures the sun during the day, it gets dark out. I don't know if you all witnessed the eclipse in 2017, but I was in central Wyoming and the street lights came on and we could see the stars. And had we made careful measurements, we would see that the apparent positions of the stars are different if you compare the position of the star during an eclipse with the apparent positions of the stars at night when the sun doesn't prevent you from seeing the stars. And this difference was measured in an eclipse in 2019 and convinced people that Einstein's theory was correct. So this is the case of something called gravitational lensing, where the actual star position is here and gets curved by the presence of the energy of the sun. And during an eclipse, we see the star here. So it was understood that light, the trajectory of light could be altered by the presence of matter. And the general rule is the light traveling in the universe will take the shortest time path. That is from point A to B, that the time it takes the light to make that travel is the time that is shortest of all the paths that are possible. And an analogy for this is the great circles that we use to fly long distances on airplane. It's not a factor if you're flying from Cleveland to Toledo, but if you're flying from New York to Paris, you don't fly on what appears to be the shortest path on a globe. You fly on a great circle. That is a circle that passes through the center of Earth. And the difference here is a 150-mile difference. And that's what light does. If it's in a curved environment, such as a space-time environment, where energy has altered the shape of that space-time environment, light will take the shortest path. That's the insight that Einstein had. Right after Einstein's equations came out, Carl Schwarzschild found a solution for Einstein's equations, which I'm going to show you. And his solution was a description using Einstein's equations for the simplest possible object, a spherical, non-rotating star. And it has the Schwarzschild result has a surprising feature. Let's look at it. Here's Schwarzschild's equation. It satisfies Einstein's theory of gravity. And the key thing is right here. Because this is a division 1 divided by something. And what this says is, if this little bit right here inside this orange ellipse, if this is 0, this whole thing blows up. You can't divide by 0. And a little arithmetic shows that this is the surface of a sphere around, centered on an object we now call a black hole. And if we take this and do some arithmetic, we find the radius of significance around a black hole, it's called the Schwarzschild radius. It has the number 2, Newton's gravitational constant, the mass of the black hole, and the speed of light squared. This is a surface around a black hole that has the property that if you're outside of this radius, you're fine. You can go do whatever you want to do in the universe we occupy. But if you're inside of this, if you pass through this region where this blows up, now you're trapped in the black hole forever. And it took 50 years to understand the significance of this little bit of Schwarzschild's equation. By the late 1950s, people began to realize, oh, this defines an astronomical object whose interior is cut off from the universe we are part of. That once you enter this surface, you cannot get out again. And there's no signposts or passport control at this surface. You're just traveling toward doom. You wouldn't even notice it, except you get torn apart by the intense gravity of the thing we now call a black hole. So let's go back to the structure of a black hole as seen in increments. If we look at a cartoon of space-time, that's all this mesh is, and we put the sun into this environment, it distorts space-time. What that means is distances that you would normally find by drawing straight lines, those don't pertain anymore. Clocks run at different speeds in the vicinity of this massive object, distorting space-time. If you take the same amount of mass, roughly, and confine it to a tiny, tiny thing, like something like the size of the city of Fort Collins, then you get a more pronounced distortion of space-time. And now we can't draw the 4-dimensional properties of space-time and project it onto a flat screen like the one you're looking at now, but a white dwarf, which is about the mass of the sun, but in a much smaller volume, would have a profound influence on the shape of space-time and the distortions in distances and the passage of clock time. Neutron star is even more dramatic, and if the mass gets big enough, you get this effect with a horizon. That's what Karl Schwarzschild's radius is now called, the horizon of a black hole. And once you pass through that horizon, you don't get out. So if our sun was 3 kilometers, or about 2 miles in diameter, it would form a small black hole. And my advice would be stay away, because once you fall in there, you're not coming back out. We have never seen a black hole this big, but next week we will talk about the new strategy we have. Actually, more than strategy, we have new instrumentation for observing mergers of black holes, or black holes swallowing neutron stars and so forth. And these are the so-called gravitational wave sensors, but that will have to wait till next week. Now I'm going to correct myself. Earlier today, I said the largest known black hole has a mass of 30 billion solar masses. Not true. 66 billion solar masses. It's in one of these references. So here's an attempt to characterize the curvature in space-time near a black hole. I've already said these things. So here's Schwarzschild's radius, calculated from basically from the mass of the black hole. Couldn't be simpler. And here's a way to think about it. Suppose you are out in your boat in a lake and you don't realize it, but somebody has put a plug in the bottom of the lake, and they yank that plug out. So water is now flowing into that drain. The entire lake is affected, but the farther you are from the drain, the less affected you are. But there is a circle around this drain that has the property that if your boat can't go faster than the water is flowing into the drain, you will go down the drain, literally. If your motor in your boat is strong enough, then you can overcome the flow of water down the drain, then you have nothing to worry about because you can putt out here all you want. And this is the idea of the event horizon of a black hole, which is a sphere around the central death zone of the black hole. Now, I mentioned before the break that black holes are black. Once one forms, if it doesn't have debris around it to digest, it is invisible. You can see it due to the distortion of distant light that passes near the black hole, so the lensing effect. But it doesn't produce any light of its own. If it has an accretion disk of debris that's about to fall in, like we are illustrating with the lake here, then you see the glow of that accretion disk, which is heated to millions of degrees. Again, this is essentially a two-dimensional fiction about how to avoid going down the drain. A black hole is a three-dimensional object. There's some examples of whirlpools and stuff. So here's a artist's rendition of a black hole. This black hemisphere represents the surface of the Schwarzschild event horizon. At the center, there's a place where nothing exists. It's called the singularity. It's where all the energy falling into the black hole resides. And here's that accretion disk I described, including the possibility, in fact, the likelihood, that there is a jet formed by the moving electric charge in the accretion disk, forming an intense magnetic field, and that magnetic field picks up charged particles and throws them out into space, away from the black hole, at near the speed of light. So there's some more details here. So this recapitulates the distortion in space-time you get from incrementally larger, more massive objects confined to smaller and smaller places. There's the black hole. So energy of any kind can fall into the black hole, and we see the accretion disk glowing, light falls in. It's a sink that consumes everything that it can get its hands on. But Stephen Hawking, you may have heard of, found in his work 15 years before he died, that black holes, because of quantum mechanics, can evaporate, but their lifetime is enormous. So this equation shows us that a solar mass black hole, one like our sun, would last for 10 to the 67th years before it evaporates. The real threat of a black hole to you and me in its vicinity is what are called tidal forces. If you're out in space in a rocket ship and you have a couple of apples, there you are, you have a couple of apples and you fire the rocket, the apple, and you let go of the apples, they will fall toward the floor in a trajectory, a parallel trajectory. But if you're near Earth, which has its own gravitational force. The force on this astronaut's hands are different. The one here, his right hand, if he drops something from there, it will fall towards the center of Earth on a trajectory like that. And the something in his left hand will fall also toward the center. So there's actually a resulting apparent force drawing the objects in his right and left hands together. That's called a tidal force. And a tidal force will do this to you near a black hole. Outside the event horizon, you still can escape if you have a big rocket. But as you descend, the fact that all the forces associated with the black hole point at the very center, the singularity, means you get squeezed this way and you get stretched this way because your head feels a less of an intense gravitational force than your feet. And this process is technically described as spaghettification. An object that comes near the event horizon gets squeezed this way and stretched this way. So people have done the arithmetic, how long you can survive in the vicinity of a black hole. And it has to do with the strength of human tissue. So let's look at the black hole at the center of our galaxy. It has a mass of 4 million suns. And your time between crossing the horizon and being at the singularity and no longer existing, all your atoms would be shredded, is about 1 minute. And you would survive for about 9 seconds. Having passed through the horizon, the spaghettification won't kill you for the first 9 seconds. Eventually, you're destroyed. If we go to a supermassive black hole, 20 billion solar mass black hole, takes over 80 hours to get to the very center. But you would survive for about 13 hours, and you could look around and make measurements and write a book and so forth, but you could never send it out to the outside world because you and your book would be inside the horizon. So there's lots of work is done. Now, I mentioned this. This is the idea that you can measure the mass of a black hole by looking at the stars and the trajectories they have around the black hole. Let's look at this. This is, what's happened? That piece of art has disappeared. I have to update that. I apologize. This comes from the gravitational group at UCLA, and what you see, these ellipses are the actual trajectories of real stars all orbiting around something right there that is the center of our Milky Way. It's called Sagittarius A star. And by looking at the shapes and sizes of these ellipses, we tease out the mass of the black hole that's there. There's nothing visible there, but we know it's about 5 million solar masses. And maybe next time I'll show you this. Oh, maybe this is the right one to go for. Yeah, no. So I apologize. I have to do some homework. But here are more details of those trajectories of objects. I mean, it looks like our solar system, right? If you look at the solar system and draw out the trajectories of Earth and Mars and Jupiter and so forth, you get ellipses. These are different because these guys all orbit that one point right there. And here's a depiction of our solar system. This is an asteroid, Sedna, and so forth. So Newton explained in the 1600s why the orbits produced by gravity are ellipses. Some of them are very close to being circles, but they're all fall in the geometric category of ellipses. But these are the trajectories of stars right near the center of our Milky Way. There's also almost certainly every black hole is a rotational black hole. It took until the 1960s to describe the mathematics of rotating black holes, but it's a unavoidable feature of the formation of black holes and their evolution. So let's look at, this is the horizon of a black hole, and this is a collection of stars and galaxies in the far distance. Hopefully this works. No. Frustrating. If you play this, you see these objects appear to be moving in all kinds of random directions because they're influenced by the gravitation of the black hole in the foreground. So I should have tested these. And the reason you see a lot of distortion is if you have your eye or your camera here, this is the accretion disk of the hole. This is the Schwarzschild horizon. You see light from this coming to you, this between this spot on the accretion disk and your camera. But you also see this light back here because it's curved, its trajectory is curved dramatically by the black hole. Let's see if we got any of this. Oh, yeah. So here's a simulation of two black holes called a binary black hole. And the simulation technology we now have requires huge computers, but it really works. And the reason we know it works is because we now have imagery of black holes taken by radio or millimeter wave radio telescopes. Now you see what's happening here. We have two black holes, and if we look at them in the plane of the blue one is rotating around this one. This is light from the accretion disk closest to us. Let's wait till they're not in. And this is light from the far accretion disk, the one on the other side of the black hole horizon. So these kinds of simulations are done all the time, and they're not just for fun. By using Einstein's equations and simulating what we know about rotating black holes and so forth, you can tease out the physics of black holes in a way that could not have been done until we had supercomputers. And you see how intriguing these are. So you can click on that. You can take a look at that at your leisure. Here's a still photo. So the black hole, the center, the singularity is right there. Here's the accretion disk in the distance, and that appears up here because of this effect. The light gets bent, and the foreground light is this part of what you see along with this. This is light coming this way to your camera. Now we have this new technology, the Event Horizon Telescope. It's based on using multiple independent telescopes where the data is all aggregated. And one of the things they see is detail that we struggle to see using other methods. Here's the Chandra X-ray telescope, and you can see that jet the relativistic jet I talked about. Here is a picture from 2019. This is an actual image of a black hole. And you can see the similarity between what we see and what I showed here. And what's more, the Event Horizon Telescope, which is an international collaboration, is not done yet. They keep taking pictures of this particular black hole. They now have two targets they look at. One is in the center of our galaxy, one in a nearby galaxy. And here's a guy, he's a neighbor of ours. He's in Boulder, Andrew Hamilton, who's one of the world's leading experts on animation for understanding, not just entertaining, but actually understanding the physics of black holes. he actually was they were planning to use him when Kip Thorne was creating the movie Interstellar, which has a lot of these kinds of animations. We can skip this. This is about rotating black holes. I'm going to skip that. But we also have mergers of black holes, and we are getting lots of data on mergers of black holes. Now, there's a section of this lecture on yet another part of the black dark universe, and that is neutrinos. These are nearly massless particles that are produced in the sun and other stars and in nuclear reactors. And this section of the lecture, you should take a look at it. It talks about the history of struggling to understand how the sun produces energy. And in the process, there were lots of problems. Eventually, underground experiments like this one in South Dakota, I think, eventually started measuring the properties of neutrinos, particles that were predicted but not seen until the right kind of sensors were invented. And we now know how to use knowledge of the neutrinos that come from the sun and from cosmic rays that strike the upper atmosphere here on Earth and produce showers of subatomic particles. Neutrinos in very small amounts are created that way as well. So we now have a theory that's very successful in describing these two numbers are relevant. We don't have to worry about what they are, but the theoretical prediction for a property of neutrinos is this prediction, and the measured value is here. So this gives us confidence that we understand the categories of neutrinos, how they're produced in the sun, and 3 Nobel Prizes were the result for finding neutrinos, predicting their properties, and upgrading the experiments so that they could all be detected. So we close out here with references to Nobel Prizes related to astrophysics and cosmology. These are 3 people I've met. And I have the autograph of Kip Thorne. It's right here, repeated here. So we're at the end. We have a little time. Are there questions? You can unmute and talk if you want, or you can put something in the chat box. If not, I'll see you next week, where we're going to talk about, it'll be the 5th lecture, and we're going to talk about the observational resources we have for doing the things that led to the conclusions we have about our current understanding of the universe. And a prominent part of that is the James Webb Space Telescope, a new resource, the gravitational wave sensors on different places on Earth. That's new as of less than 10 years ago, and other telescopes that are coming online to help resolve issues related to dark energy, dark matter, expansion of the universe, resolving the Hubble tension, and so forth. So with that, I will see you next week, and I wish you a good day.